Hello and welcome to volume number 3 of my data center technical series. Today we're going to be reviewing the Coup de Fouet, or the tail of the whip, the battery discharge curve on valve regulated lead acid batteries, or vented lead acid batteries, or nickel cadmium batteries, or even lithium ion batteries under intercalation. So when we're looking at the state of charge on a battery system, you can see right there 13.5 VDC. That float voltage is not indicative of the state of health of the battery system. I often use an analogy when I'm looking at batteries and testing and commissioning them around the world is I have no idea how fast you can run a mile. So what I need to do is make you work. And how we do that with battery systems is by put them under a DC load bank, under a DC resistance for DC current. But if I wanted to average you out, if you're running different 1,600 meters, what I need to do is have you run 1 mile at 6 minutes, and then have you run 2 other miles after that at, as close as you can at 6 minutes. Now I can implement an averaging algorithm. But from here, what we need to do is we actually have to load the battery down. So on a 13.5 volt monoblock or 54 volt load step group, what we need to do is actually load this down. You're looking at a voltage coefficient. So we can actually take that, subtract it from V1, and then divide it from here. That will give us that time delay from the discharge curve here on the Coup de Fouet, the tail of the whip, as you can see. But what we're going to do is actually measure that voltage at the bottom. We're going to label that as a V1. Then we're going to release that voltage up into V2. So from now we have a delta V. That's actually the voltage reflection under load. So we're going to take that V2, subtract V1, and then we're going to put that over a current. That's simple Ohm's law, right? So if we're doing simple Ohm's law, we should be able to just do V, I, R, right? And if I want any one of these, if I want, resistance here, basically I would just take that delta V and divide it by the current, which is what we're doing right here. That's what you can see. And that's going to give us internal resistance in micro-ohms, particularly on valve regulated lead acid batteries, but in many different types of systems. It's the same kind of thing if you're testing cables, intercells, you're inducing a voltage reflection, and then you're measuring that and putting that over the induced current. This is the only way to effectively measure and establish a baseline for DC batteries. I've always wondered this throughout the industry. Now we have so many different other types of monitoring technologies, and I will review that hopefully after this video, or I'll create a separate one based on AC impedance and AC conductance and so on and so forth, a few of those other variables, and they're very different than DC current, because if you're going to have a DC system, a 540 volt DC bus on a 750 kVA UPS or 1 megawatt 3-phase UPS, you need to understand how to test this effectively. The DC bank is outputting DC current into the inverter. Why would you test a battery system with an AC signal source, AC impedance, a voltage, or an AC current? And there's a lot of problems inherently in testing bigger battery systems with AC signals. Number one, you have capacitive reactance. I think there's a formula, 1/2 pi, I believe it's, 1/2, I think it's pi times F of C, and F is actually the frequency of the testing device, and C is the capacitance of the battery, right? So it's very important when you're looking at this. What this essentially means, if you're using an AC-based meter, is the bigger the battery system, the bigger the amp hour of the battery, the lower the resolution if you're using a single frequency testing methodology. Now, I'm not talking about spectroscopy here, which I fervently believe in, because that is inserting several different frequencies across the anode, the cathode, and the material science of the battery system. I think that's probably something we should be using moving forward, because it's going to catch a lot of other failure mechanisms. But AC impedance and conductance, in my opinion, generally only finds certain types of battery failures, or a battery that is now open. It's not going to find a degraded battery over time. There's also a secondary problem with using AC signal sources, and we'll get into this as we review harmonics and noise and switching mechanisms from the instantaneous gate bipolar transistors or the silicon controlled rectifiers, SCRs, 6 pulse or 12 pulse. Depending on your configuration and UPS and your efficiency of those devices, it can cause a higher level of noise. The noise floor in the DC bus can be much higher than the signal source of an impedance or conductance-based meter. And I'll give you an example. Let's say a conductance-based meter or impedance meter is injecting a 1 amp AC sine wave across the battery terminals. Well, if you have 5 or 6 amps of harmonics, AC harmonics riding in the DC bus, either feeding back through the switchboard power supply through the inverter, sinking back into the battery system. Now the noise floor is 5 amps, but the signal you're injecting with those small meters is 1 amp. So what happens to the resolution? It disappears. It gets lost in translation, and that's really important to understand because depending on these systems, especially older systems, noisier systems, it's not going to effectively find a defective battery in time. Now, this doesn't apply so much to DC plants because the noise on DC plants obviously is exponentially lower than 3-phase power systems, bigger 3-phase power systems. But it's very important to understand these principles when you're looking at battery monitoring across the entire spectrum and why we only use DC resistance testing at nuclear facilities, at the Federal Reserve, at DISA, at a lot of other places like that, because it's the only proven method to find degraded batteries and a trend. And what we generally do is this resistance here that we're inducing from the DC load bank, if we're doing 54 volt load steps, generally in a 540 volt DC bus, you would have 10 load steps at 54, and then this load bank would probably be about 1.6 ohms, right? So if you use Ohm's law, very simple again, you got 54 volts divided by 1.6, what are you getting? You should have about 30 amps. And that's pretty amazing. It's simple stuff that you can look at, you can implement, you can show, you can discuss and review. And again, as you're looking at these systems and battery technologies, if you don't understand how we test them effectively, then you're never going to know when there's a bad battery and it could cause an outage. Now, in battery systems in general, we also look at inter-tier resistances and intercell resistances. Same methodology, we're looking at the voltage drop across the cable, 100 millivolts, 200 millivolts, 300 millivolts, et cetera, et cetera. The inter-tiers are generally the cables that go from rack to rack or tray to tray in a cabinet system. You might have 10 different trays of 4 batteries per tray, and we need to measure those resistances accordingly, because also during under a discharge, we have to add that voltage drop back to the cell input channel. Otherwise, you would see, every 4th or 5th battery, 80 to 100 millivolts low, and it will look like they were degraded batteries. But it's actually, you didn't calibrate the inter-tier channels appropriately in accordance with manufacturer specifications. Now, also intercell resistances are the cabling between each individual battery, right? So you'd have a negative, positive, negative, positive, negative, positive on a battery string, and you need to understand what those resistances are, because if someone misses a torque during a quarterly periodic maintenance or an annual periodic maintenance, and then you undergo a discharge test, let's say 600 amps, going through a resistance that generally was maybe 5,000 microohms and now is, 30 k ohms, that's significant, because that huge difference of potential and increased resistance is going to cause an increased exothermic heat generation on that terminal, and you do not want high level exothermic heat anywhere near the battery. That's what causes thermal runaway. Okay, so this is really fascinating. I love discussing voltage drop and voltage coefficients or reflection coefficients, but also internal resistance. Again, let's review. You take that difference, V2 minus V1, and you put it over the induced current, and you're going to get your internal resistance in DC. This is very simple, but I also want to review something else that many different companies out there are doing, but they're not telling you, is an averaging algorithm. So I find this all the time when I go out to different facilities, is that this same system here, depending on how the rectifier and the charger is set up, because it's constantly jumping, right? So when you take this measurement here and here, the charger is trying to equalize the DC bus. So if you're testing in load groups of load 1, load 2, load step 3, load step 4, this can jump around quite a bit. It can cause it to become erratic. So ask your vendors, your battery monitoring manufacturers, if they are utilizing an averaging algorithm. And if they say no, or yes, ask them to elaborate, because this system can also degrade batteries in a DC current implementation. Why? How can this do this? Well, instead of just doing one of these voltage drops like this, what it would go out and do is 5 to 7 or 10, and then drop the 2 highest and 2 lowest and average the middle 6. And this again is trying to make up for inconsistencies, inadequacies, and inefficiencies in three-phase UPS power systems, and it can cause quite a few problems. I've even seen this cause early grade battery degradation and failure, because generally what this is doing is you're hitting the battery over and over and over and over again. It's cyclical, and the battery discharges are rated, maybe for 1,000 shallow discharges and 2,000 shallow discharges, depending on the battery, and depending, it could have a larger depth of discharge. Now they say that this doesn't get into the chemical portion of the battery. How do you know that? How does anybody know what's going on inside of the battery? All I know is if you load it consistently with an averaging algorithm that's hitting it 7 times on the cell and 250 times on the integer because of a noisy DC bus, you're definitely going to vent excess hydrogen. And we talked about this in the previous 2 episodes. If you are, expelling excess hydrogen, then the conductance, the conductivity of the battery decreases, because the glass matting, the insulation between the 6 2-volt cells of the battery decreases exponentially, right? It vents that hydrogen, it loses water. It's 95% recombinant anyway through that one-way pressure valve, 5 to 7 pounds per square inch. You keep losing hydrogen, you're going to lose water. You can't add water back into this. There's no reservoir for that. You can do it on vented lead acid batteries, so flooded batteries aren't as big of a deal, but on VRLA batteries, it is significant. So thank you so much for paying attention to Volume 3. I'll keep diving in, and I appreciate you tuning in. Have a wonderful day.